All right, so the first step when you run any StormCAD model is that it calculates the hydrology because our beginning point is we need to know the flows that are going to be coming into the system. And knowing those flows, we can then figure out, um, like Q equals VA, right? So we know the area, now we know the velocity, right? So we can figure out from the flows, we can figure out velocities, we can figure out normal depths, we can figure out friction losses, we can figure out hydraulic grade lines, energy grade lines, etc. And how that's all happened, we're going to learn. Well, we talked about this before. It's that everything I'm going to say to you today applies to the StormCAD solver, which is the GVF rational. Okay, so when we talk about flow in general, we can be talking about open channel flow, which is flow with free surface exposed to the atmosphere. And basically, what makes the water move there is gravity. So most storm sewers are designed this way. So because it doesn't cost anything, the water just flows via gravity. Whereas in other systems, you have to pump it, and that becomes more work. So we like gravity. So we aim for open channel flow whenever we can. Uh, you might have also intentionally designed parts of your system to be pressure flow. So it's a flow that is going in a closed pipe like this, and it's under pressure. But for our case, we are going for the open channel flow. So that's what we should keep in mind when we're thinking about StormCAD. So because that's the way that it's supposed to be designed, we use all the hydraulics of open channel flow in StormCAD. Um, we know that if you were to look at a pipe and you were to measure the velocity and you look a cross section of flow, the velocity wouldn't be the same, right? The velocity of the top of the surface versus the velocity against the friction would be slightly different. So what we refer to, we couldn't possibly calculate the velocity at every single spot in the cross section. I mean, we have to be a little more practical than that. So we go with average velocity. And how do we come up with that? Well, we know that velocity equals flow, which remember we've already calculated from the hydrology, divided by the cross-sectional area of flow. So it's not just the area, the cross-section area of a pipe, but it's the cross-sectional area of the flow. We're going to talk about is the wetted perimeter um, of a pipe if it's not flowing full. And then we use that and we just rewrite the equation. We say, okay, we know all these terms. Now what I know that I know Q and the area, if it's a circular pipe, then I can say that the area is P R square, and then you make that um, so that it's only in terms of the diameter, which you already know because you've input. So now we can figure out the velocity. All right, so we go on like that, and then we start using a whole bunch of equations to come up with every single one of our values. But before we start just talking about equations, let's get some terms straight. Those gradually varied flow solvers, like the one in StormCAD, evaluate steady and non-uniform flow. So what does that mean? Steady means that the flow properties do not vary over time at a point. So that if I'm looking at this pipe right now in my peak conditions, the flow properties are going to be the same. In other words, it's like we're taking an instant photograph of the system. We're not looking at what happens at 5 o'clock in the morning and then how it changes from 5 to 6 and then to 7 to 8. No, we're just looking at one point in time. That's what we mean by steady. And non-uniform um, basically means that the properties of the flow vary or not vary in space. So we're saying that the StormCAD solver is capable of taking that instantaneous picture, so doing that steady flow, and also looking at how properties of the flow can vary because there is some type of control. So you can have, um, like a weir or maybe the slope change or something changed that made those properties not be uniform, right? So non or uniform flow is a very simplified type of flow, which is non-accelerating, it's steady, it's going through a prismatic channel. Prismatic meaning something that has a constant cross section, constant roughness, constant slope, that the streamlines of flow are parallel, that the pressure distribution is hydrostatic, that the flow depth is always the normal depth. So really like these ideal conditions that don't exist in the real world. However, we do use uniform flow to assume what is the capacity of a pipe. So only when we do channel capacity do we look at uniform flows. Most of the time we're looking at the non-uniform flow. So again, like we have things that make the the flow change in space. All right, so how do we solve all these complicated networks? We use a series of conservation principles. So conservation of mass, conservation of energy or momentum. Conservation of mass simply says that anything that comes in has to come out. So there's got to be continuity of flow. And the way we do that is we say if there is no storage, so at any particular node, whatever comes in has to be what comes out. Um, but there's a possibility of storage in that node. So if there's a difference, it has to be due to storage. It can't just disappear. And then the conservation of energy, it's basically the application of our Bernoulli equations, right? So we know that the water is going to flow from a region of higher energy to a region of lower energy. And in order to measure that energy, we look at head. So we measure everything in feet or in elevation. And typically we talk about either hydraulic grade line or energy grade line. And that represents the total energy of flowing water in a pipe or channel. And the hydraulic grade line is the sum of only the pressure and elevation head terms. So if we're looking at non-pressurized flow, we're simply looking at the Z value, right? The elevation head plus the normal depth or the depth of flow, right? So that's our hydraulic rate. So basically it's the water level. So when you think of gravity flows, hydraulic grade line is pretty much the water level. But energy grade line is includes the velocity head. Remember, v squared divided by 2g. So that's the difference between the energy and the hydraulic grade line. And here it is in a little graph. So if we have our pipe, the center line of our pipe is where we are taking that z value. So we know we're comparing point 1 with point 2. And at point 1, we know that we have a z component, we have a pressure component, although if it's in our case, again, there is no pressurized flow, so we're going to ignore that. And then the v squared divided by 2g, which is the velocity head. That's what gives the energy grade line. And the hydraulic grade line, again, is the same as the energy grade line without the kinematic component. Okay, so for full pipe flow for pressure, this is what we would have, that if you compare point 1 with point 2, there is a difference, and that difference is the head losses due to friction. So to move the water from point 1 to point 2, we had to spend some energy, and that is calculated as friction head losses. And there are different equations. We're going to briefly take a look at all the different methodologies for calculating that. But here in our case, for open channel flow, uh, again, we know that if this line here represents the bed of my channel, I have the elevation at each of my points, and then there is no longer a pressure component, so it's simply the depth of flow. That's what this Y1 represents. And then there's also, as the flow is moving, a velocity head component. So really, the only thing that changes is that instead of pressure, we have the Y, or the depth. And just like we have in general hydraulics, and if we're looking at moving one or flow from point 1 to point 2, if we were going to compare it, there comes again the energy that gets lost to move it from 1 to 2, which is our head losses due to friction. There could also be minor head losses, and we're going to talk about that in a bit, but they're so small compared to the energy that is lost due to friction that sometimes we just kind of talk to them about, we say head losses without making the difference between minor and friction. Okay, so how does that component get calculated, that head loss due to friction? Well, as I mentioned, is the friction head loss is the energy used to overcome friction. There are different equations. Depending where you are in the world, you'd be more likely to use one or the other. If you're in the US and you're dealing with open flows, most of the time you're talking about using the Manning's equation. If you're in Europe, probably Darcy-Weisbach. Hayes and Williams is for pressure flow, so we don't even think about that. And again, the majority of head losses is due to the wall friction, and the minor losses in comparison are often small. So what is that Manning's equation? It's listed here. And basically what it entails is that you find from a table the Manning's roughness coefficient. So we know that's an input that you have. And we have already from our hydrology calculations, we already know the flows, we know N, this is just a value, we know the cross-sectional area flow, and we use that to calculate the slope of the energy line, which in turn tells us, how much energy has been lost due to friction. So what is that N value that we entered? Well, it's influenced by the factors that you see here. So depending on the roughness, most of the time if you're looking at systems, or pipe systems, you know that the N number for PVC is 0.013 or for different values. So most of the time you associate N with the material type. But if it's natural channels or things like that, vegetation and other things come into play. Here are some of the N values. You can find this table in the help or anywhere if you just Google it. Here's another equation that it's not very used in North America. It's not commonly used. It's more in other parts of the world. And it's actually kind of a similar equation because you take into account the length of the pipe, the diameter, and the velocity, but then the F factor, unlike the Manning's coefficient where you simply look up an N value and you input it here, the F value has to be calculated from this Moody diagram. So you need to know the relative roughness, that's basically the number that you would input into StormCAD. You calculate the Reynolds number, and here's where things become tricky because this is kind of a moving target because as flows change, velocity would change, so the Reynolds number would change. So it's not like you can make a direct correlation. But once you know the relative roughness and the Reynolds numbers for that particular condition, You would go into that line, find the intersection, and then figure out the friction factor. But that just makes it a little more complicated because it's not as simple as just inputting an N coefficient. Um, so here are some examples of that relative roughness that you would use if you were using that friction method. And here is the Hazen-Williams friction head loss equation. This is used for pressured flows. And C is function of pipe material, and H, you just look it up in a table again. All right, so we've basically established that most of the time we're going to be using Mannings. You're going to be using Mannings in the US. And so that takes care of figuring out the head loss due to friction. But there's also the possibility of the minor losses. Anything that exists in a pipe or in an open channel that can cause the flow to accelerate, decelerate, change direction, change cross-sectional area, it results in an added loss of energy. And this is how we calculate the minor losses. We use a coefficient and we multiply times the velocity head because the velocities are usually so slow, and then we square it like 0.5 meters per second, and then we multiply that. It just gets to be 0.025, so it just gets even smaller. But having said that, you still do look at these minor minor losses. In particular, for our example and what we're going to be doing, we're going to be accounting for losses. Besides the friction losses, we're going to be looking at losses in your structures. Okay, so this does come into play a little bit later. We have another presentation on that. Okay, so we said that StormCAD takes into account the non-uniform flow because flow does vary in depth along your channel. So depending on the downstream conditions, changing slopes and things like that, your depth does not remain the same throughout the channel. In fact, most channels are non-prismatic. In storm sewers, we have things like manholes, changes in diameter, slope, and direction. So all that makes us having to analyze our flow at each. Basically, we break a pipe into little segments and we calculate for each of those segments what the depth is, and all those basically run hydraulic calculations on each of those little segments. In addition to those normal things like manholes and changes in directions and things like that, we have weirs. We could have things like weirs, free outfalls, flumes, or other types of controls that would alter the hydraulics of our system. So we can input those as well and have the software calculate those for us. So we're not going to go into a whole lot of depth in here, but when we're doing gravity systems like this, we are always looking at profiles, right? We want to make sure that everything is looking smooth, there's no surcharging, but we're also looking for what kind of profile is this? So is the slope critical, mild, steep, adverse, and horizontal? The software does this calculation for you, and in fact, at any pipe you can click and it tells you what kind of flow profile it is. But most of the time we're concerned with flows going from subcritical to supercritical. So if you have very rapid flow that, I don't think I have a picture here, but if we have, put a little drawing here. If you have a situation where you have your channel like this and maybe it changes slope, so it goes like this. Oh, I don't know what happens to this pointer. But anyway, so the flow is very shallow and rapid moving here, and then it just kind of goes like that. In this location, there could be a problem with the formation of hydraulic jumps. So we like to look at our profiles to try to avoid things like that. And the software can actually tell you what your flow profile would look like, and you can actually see it drawn on those profiles. So how does it, knowing all these conservation of mass, conservation of energy, how does the software come up with the solutions? Well, there's the direct step method and the standard step method. And both of them basically involve dividing the channel into little segments and then solving for either depth or length of the segment. The direct step method uh, assumes a depth and then solves for the length of the segment, whereas the standard step is the opposite. So it knows the lengths and it solves for the depths. The StormCAD solver uses the direct step method. All right, so again, in summary, we use the rational method to come up with flows. Then once we have the flow, we figure out hydraulic rate, and we use that using the gradually varied flow methods. And is what that GVF storm solver looks. I'm not going to go into a lot of detail, but I just want you to take mental picture of this to realize that SewerGEMS, CivilStorm, all other Bentley products have more options for solvers. And the one that we're concerned with, which is a GVF rational for steady non-uniform flow, is found in SewerGEMS, CivilStorm, and StormCAD.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.